All right, let's just dive right into this. Before we go anywhere else today, I want you to do a quick mental inventory for me. Just look around you right now. How many devices do you personally own that are plugged in or charging at this exact moment? Seriously, think about it. You've got your phone, your laptop, maybe the Wi-Fi router humming in the corner, those wireless earbuds, maybe the smartwatch on your wrist. Take a second and just tallying that up in your head. You probably have quite a few things drawing power right now, don't you? Okay, now take that personal number you just calculated and multiply it by 4 billion people. Yeah, suddenly that handful of devices on your desk transforms into this incredibly massive global digital footprint. And this simple multiplication exercise perfectly sets the stage for the massive scale of what we're looking at today. It connects your everyday personal device habits directly to a sweeping global reality. So, welcome to our explainer. Today, we are breaking down a really fascinating source. We're looking at the introductory syllabus for CSE 407 Green Computing. The title for this opening class is The Importance of Green Information Technologies. And the core message right out of the gate is loud and clear. Energy efficiency in computing is no longer optional. It's an absolute must, and engineers at every single level can make a measurable difference. The source explicitly notes that this isn't just another easy elective. It is highly practical because the systems that engineers build consume real energy, they produce real carbon emissions, and they generate real physical e-waste. To tackle all of this, here is our roadmap for today's explainer. 1. The massive energy problem. 2. Decoding green IT tracks. 3. Essential terms and math. 4. Global and local drivers. And 5. The engineer's role. Starting off with Section 1, the massive energy problem, focusing on IT's growing energy demand. To truly understand the sheer size of IT's energy consumption, we really have to look at the macro-level global math. Right at the top of the curriculum's dashboard, which basically serves as a high-level view of system-wide metrics, before we even get to the reading list, the course lays out 4 terrifying statistics to frame the entire scope of the problem. Let's break those down. The very first alarming stat on that dashboard, approximately 2% of all global electricity is consumed by data centers alone. I mean, think about that scale for a moment. Every single time you stream a video, or back up a photo, or query an AI algorithm, you are pinging a data center somewhere. And those centralized hubs are drawing an absolutely immense 2% of the world's entire electrical output. And the situation is absolutely not standing still. The second number on the dashboard is 4x. This represents the faster IT energy demand growth versus our grid supply. What this means is that the energy our IT infrastructure demands is growing 4 times faster than the power grid's actual ability to supply it. We are literally on a trajectory where our technology's appetite is just completely outrunning our infrastructural capacity. But honestly, it gets worse because we aren't even using that power efficiently. The third stat reveals a massive inefficiency. 40% of data center energy is wasted purely on cooling alone. That's almost half. Almost half of the energy pumping into these massive facilities isn't even running computations. It's going straight into industrial HVAC systems and massive water cooling pumps just to keep those dense server racks from physically melting down under their own thermal load. So the crucial point is summarized in this final rapid-fire statistic. IT is responsible for 3% of global greenhouse gas emissions. When you combine the massive global power draw, the hypergrowth that's outpacing the grid, and those extreme cooling inefficiencies, it culminates in a very real, very physical 3% chunk of all global emissions. The digital world has a very heavy physical cost. Moving on to Section 2, decoding green IT tracks, looking at the 2-track structure. So, the syllabus tells us that the course runs across 22 total classes and is structured very meticulously into 2 complementary tracks. To navigate these tracks, the course relies on 2 specific cornerstone textbooks. The readings pair Chapter 1 from Velta's book, appropriately titled Green IT, with Chapters 1 and 2, specifically pages 15 through 30, from Lamb's The Greening of IT. This dual-track approach is great because it ensures engineers get a really comprehensive, multi-angle view of both the core theory and the real-world application of green computing. All right, Section 3, Essential Terms and Math, focusing on key concepts and terminology. Because to solve those massive math problems we just looked at, engineers need a standardized vocabulary. One of the absolute foundational terms you have to master here is PUE, which stands for Power Usage Effectiveness. This is the exact mathematical formula that engineers use to measure that 40% waste we talked about earlier. It's calculated by taking the total facility energy, so that means everything, including the lights, the security cameras, and yes, the cooling, and you divide that by the IT equipment energy, which is the power used by the actual computing servers. A perfect score is 1.0, but in reality, most facilities score much, much higher, which just highlights a massive amount of energy waste that engineers need to step in and minimize. And then, of course, we have the carbon footprint. Within this specific IT context, it's defined as the total amount of greenhouse gases generated by IT actions and e-waste. This perfectly bridges the gap between abstract computer code and real-world environmental degradation by splitting it into two distinct parts. First, you have operational carbon, which refers to the emissions from generating the electricity to run those servers day to day. And second, you have embodied carbon, which accounts for the massive environmental toll of manufacturing all that hardware in the first place and dealing with it as toxic e-waste later on. Which brings us to Section 4, Global and Local Drivers, exploring why organizations adopt green IT. The source outlines 4 specific forces that are making sustainability a top business priority today. And it's crucial to understand this. Businesses aren't just doing this for good PR. They're literally being forced to adapt. They're facing impending government regulations, shifting market forces and investor demands, growing social and public pressure, and, well, the stark reality of our environmental limits. These 4 forces combined are compelling businesses across the globe to treat green IT as a mandatory core business strategy. But what's really fantastic about this syllabus is that it doesn't just stay high level and global. It features a specific module on green IT in the Bangladesh context. This highlights that the macro forces driving sustainability have profound, immediate impacts depending entirely on your local region. It matters deeply for engineers to understand the specific environment they are operating in. For example, if you're dealing with developing nation grid constraints, rolling power blackouts, or the extreme cooling challenges of trying to run high-density data centers in a tropical climate. Context is everything. Finally, Section 5, the engineer's role and practical application. We have arrived at the most crucial part of this explainer, what you, as an individual, can actually do about this. The course outlines 3 core actions, or learning goals, that engineers must execute. Number 1, understand energy consumption. Number 2, measure carbon emissions. And number 3, minimize real e-waste. This brilliantly illustrates the entire arc of the syllabus. It moves you logically from understanding the massive global problem to measuring it with technical formulas like PUE to finally taking concrete, measurable steps to minimize that impact in your daily engineering work. And that brings us to the final wrap-up of this opening lecture. The course leaves its students, and I am going to leave you with a highly provocative question. Every specialization has a green lever. What is yours? Think about it. Whether you are a software developer writing more efficient code, a hardware engineer designing lower power chips, or a network architect optimizing data routes to save power, you have a lever. Now that you understand the staggering math of our digital footprint, how will you use yours?